How was your day?
It's all good.
Good.
Just a bit cold.
Are you used to rain in your country? Does it rain very
Yeah,
often?
there's only two seasons, rain and dry.
Yeah.
Yeah, that's the only season.
You're from
Cambodia.
Cambodia, huh? Must be very green, is it?
Yeah.
All right. So here are the grades, and here is Mr. Chaisal, and okay. So this is your first track. This is your second track. I've marked both of them. So you're right. You did submit them, but let's see if you have done the snapshot for web calculator.
Hmm.
No, no, web calculator. Web calculator, when it shows the deform structure.
Oh, you want me to include that? No.
Yes, yes. These are
I thought just I thought just go on.
the results, huh?
Yeah, can you go up a
Well,
bit?
I just wanted
I
to.
thought you just want this one.
No, this is nothing. That doesn't show the deformation.
Oh,
So for every case you solve, you get distribution of the forces, internal forces.
yeah.
So you want to show that, look, this is the maximum tensile load. How can I check this from this image? It doesn't have anything. This is just a geometry. No load, no deformation, no forces,
Yeah.
right?
My bad.
All right.
I should. I did it, but I.
Yeah,
Yeah.
yeah. Yeah. So that's okay. That's okay. But I see that many people haven't done their submission, and that makes me worried. So if I go to the grades, and here, this is Prak. So Daniel, Abdullah, Ahmad, Nijil, Barnaby, Shah, yeah, they haven't done these reports, not to mention Serish. All right, let's wait for everyone to come.
Thank you.
All right. All right. Today is we will be running demonstration, and tomorrow is for the third lab. And let's go to page 358. Okay, 358. And here we have some problems regarding average stresses, whether they are shear or normal. Let's take the Okay, we'll start with problem 7-3 that is on page 358. Can you see it from there? Is it visible? Okay, so here you've got a bar, and in this bar has a number of point loads, and so as a result, the normal stress is not constant through the bar. So if I choose to make my section between B and A, or between B and C, C and D, or C and F, for each, the internal force would be different. All right, so let's just find out if I make that is AB, and that is the free body diagram. I'm looking into the right-hand side free body diagram. This is for BC, and that is for CD, and that is for DF. All right. So when I make the section at AB, the free body diagram looks like for AB. The free body diagram is like so. This is A, and that is 10. So the left-hand side, hello, right-hand side is going to be equal to that one, 10. Okay. And so here, FAB is equal to minus 10. That means the member is under compression. So when we make the free body diagram for BC, then you will have a free body diagram with 10 here and 6 here. And then here I need another 4 to make this at equilibrium, right? 4, 6, 10, 10 cancels 10 from right to left, left to right. So here I get the internal force of BC is equal to minus 4. That is also in compression, compression. And if we make the free body diagram between CD, so that is 10, 6, and then you have a 2 here. So I need another 6 here to make this as balanced, right? So here, that is section 2 and 10 is 12. So 6, another 6 makes this 12, 12. Yep. So this is FCD. Minus 6, again compression. And finally, if I make a free body diagram at DF, so that is 10, 6, 2, 5. So that is 12, take away 11, that you get 1, right? So here FDF is equal to minus 1 in compression. All right, so the largest internal stress would happen where? The largest internal stress develops between A and B. So here we got the largest internal force, largest internal stress, because the cross section doesn't change. The cross section is the same. All right. Question. You want this, or can I go to the next question? Clear? All clear? Seven dash 4. Do you want to try this one yourself, or should I start discussing the problem? So here the axial force is a distributed. That's a load intensity, but that is in the x direction. The unit is kilonewton per meter. Hi, Darcy. Morning. So what did you miss, Darcy? We had a bar which was point loaded at different points, and we wanted to find the largest internal force. So we made a number of sections, for each section making a free body diagram, and for each you find the internal forces. So between A and B, you got -10 compressive. Between B and C, -4 compressive. Between C and D, -6 compressive, and between D and F, -1. So the largest internal force develops between A and B. All right, this one, maybe you want to think about that for 2 minutes and let me know if you have an idea how to approach this one. Well, Abdullah. Okay, if I want to make a section at A, do I need to find the reaction at the valve, or just can I take the free body diagram at the right hand side? So my question is, am I able to simply cut this from here and right hand side solve the free body diagram, or do I need to find the reaction here first before I make a free body diagram? Sorry? I can cut it. Agree? Yes, Darcy is correct. So what happens when I cut this at point A? I have only a portion of the distributed load for the length of 3 meters. So for that 3 meters, 8 kilonewton multiplied by 3 meter, that is 24 kilonewton. So where should I place that force? I mean, it doesn't matter, but basically if I want to concentrate that force, should I put it at the beginning, at the end, in the middle? Where? In the middle, right? We know that, hello. We know that the resultant force can be lumped in the center of the shape. So this 24 comes here, and then I have to add a reaction force at A. Generally speaking, we assume that it's in a positive direction, but because there's only one force, I know that the force has to be this direction to cancel that one, right? So here Fa becomes 24 kilonewton. Okay, with the newcomers, we are going to have the last laboratory tomorrow, as we agreed. And hello, Flynn. How are you? Daniel, is it? Daniel, Flynn? Flynn, yeah. Sorry about that. Um, all right, so what you missed here, we are discussing the average stress. Average stress could be either the normal stress when the force is perpendicular to the cross-sectional area, or if the force is coplanar with the plane, the stress that develops is shearing stress. So in this case, I have a bar which is fitted to the wall, fixed at one end F, and it has a number of point load at different locations. What happens if I investigate the variation of the load in different sections? So between A and B, B and C, C and D, and D and F. So all it takes is you have to do a number of free body diagram from right hand side, and by solving each you find the internal forces. So this is the internal force here, that is the internal force here, this is the internal force there, and that is the internal force there. All of these internal forces happen to be making the part in compression, and the largest internal force is -10, that is between A and B. Okay, so the next question we did was we had a bar fitted to the wall. This time, instead of the point load, you have a distributed load. That distributed load, how do I know? Because the unit is kilonewton per meter. So in this case, I only want to find the internal force at point A. I don't need to calculate the reaction force. Simply by cutting through A and taking the right-hand side free body diagram, that is enough. So the next step, that portion of the distributed load only over 3 meters has to be concentrated, which is 8 multiplied by 324 kilonewton, and that should be located right in the middle of the part, center of the area. All right, so those who haven't done their report for the lab, these labs are very important. I notice some people still haven't submitted their lab 1, lab 2, so that's altogether 20%. I don't know what you are counting. Maybe with the mid-semester exam, I shouldn't be that generous. So look, take this serious. You can't afford to miss 20%. All right. If you need to make a late submission, just let me know and I see what I can do. All right. And then when you are making the report, only few people got the report right. I mean, I expected to see the snapshots from the web calculator. So if you did it, I need to see the result too. If you don't include them in the report, only I think Darcy report was complete. Aiden's was good, but with the others, they were very concise report, no showing of the snapshot from the web calculators. These are important because you want to compare. So your hand calculation, some of the report didn't have the hand calculation nor have the snapshot from the web calculator. Is that clear? All right. Okay. Any question? Let's go on, and now we go to page 359. All right, 359. I've got 7-7. So that's a interesting one, and maybe you could give this a go before we try that together. Can you see it from there? So let me summarize the input for you. AB and CD, they have a cross-sectional area of, so DAB, not DAB, AAB. So the area of AB, that is 10 square millimeter, and the area of CD is 15 square millimeter. Okay, so this intensity, we want to find that such that the normal stress in AB, we want that to be equal to normal stress in CD. So let me explain. Having the normal stress being equal doesn't mean the internal forces are equal. Because they have different cross section. One of them is thinner, one of them is thicker. So to make the normal stress equal, that means the internal forces should be unequal to compensate for the cross-section difference. So I would be happy if someone can tell me what the steps you reckon should be taken. Nguyen, what should we proceed? What is the first step? Shah, what is the first step? Speak up. Distributing the load to find the you mean changing the distributed load to the point load, and then what? Chase out. What is the first step? Well, just what is the formula for the stress? The formula for stress, for example, the stress in AB, that is FAB divided by the area of AB, right? So area of the AB you have. What is missing there? FAB. How do I find FAB?
Find FAB. Is given the maximum normal stress.
Yep.
So put it in there, find FAB.
So the board I'm waiting for is calculate the reactions. Once you find the reactions are internal forces inside AB and CD, right? If you find the reaction, that means you know how much internal force. The next step is internal forces should be converted to internal stresses. So, yes, you're right. To find out the reactions, I need to lump the forces first. And that means this is 6 meter, 1/3 from the base, that is 2 meter. And that is 2 meter from here. And the area under the triangle is W multiplied by 6 divided by 2, that is 3W. Correct? That's the area of the triangle. Is the total load. If I want to lump the distributed load into a point load, and the line of action is 2 meter from the right or 4 meter from the left. That is the center of the triangle. Everyone with me? All right. So the next step is I have to cut this or release this from here. So now my free body diagram is an envelope which is taking that part of the structure, the lower part of the structure. And for that, I need to expose the forces at the cutting points. So it means you're going to have the force, the internal forces exposed at the cutting point. This is FAB. And this is FCD. All right. So remember from free body diagram how these forces can be calculated. What is the best condition to apply. There are three conditions, right? So the net forces horizontally equal to 0, that is not telling me anything because all forces are vertical. Net forces vertically equal to 0, that is a useful equation, but still, if I write that condition, it gives me two unknowns. So what other condition I can use? Rotation, and rotation about where? What happens if I take rotation with respect to the A? So net rotation with respect to A equal to 0, and that is my positive direction. So that would vanish the FAB, and then you have 3W times 4 in the negative direction minus 3W multiplied by 4. And then this one, if that is tensile, that would be in a positive direction, plus 6 FCD equal to 0. And then 1, 2, 1, 2. So therefore, FCD is equal to 2W. So the next step is, now that I have FCD, it's easy to find FAB because the net vertical forces are 0, 3 down, 2 up. AB would be 1W. 1W plus 2W is 3W. We cancel that 3W here. So that's one way of doing that. Or you could write the net rotation with respect to point C equal to 0. That also gives you the same answer. So either I go with net rotation with respect to the C equal to 0, or I go net forces vertically equal to 0. Both of them, they give me FAB is equal to W. All right, what should I do next? Now that I have forces in terms of W, the condition which we are looking for, we want to make the stresses equal. So let me construct that equation here. Sigma AB. Sigma AB is FAB divided by area of AB should be equal to FCD divided by area of CD. So where did I get this equation from? That is the condition we were looking for. We wanted the load intensities to be equal in both members, right? So this one, just plug the numbers. FAB is W divided by, what is FAB? FAB is 10. That should be equal to FCD is 2W, but then the area for CD is 15. All right.
Is that what the question is asking then? Because I read
They want you to find.
They both just have to be less than 300. Not
Sorry?
necessarily equal. I thought that both of them just have to be less than 300, not necessarily equal. That's the way I read it, but I might have just read it wrong.
All right, so let's see. Yeah. You don't want that to exceed 3. I didn't read the last part.
Yeah.
You're right.
But they don't actually have to be.
So they should not exceed 300. Because this equation, I don't think you can solve it. Because you cancel W, then 1 over 10 is 2 over 15. That's nonsense. Yeah. So thank you, Aiden. You're right. So that condition is not right. The condition is the largest value of the stress should be still smaller than 300. So in other words, you want both sigma AB less than or equal to 300 kilopascal, and sigma CD is also smaller than 300 kilopascal. So here, okay, so now I'm applying the conditions. The first one is normal stress in AB, and this is normal stress in CD. For that to be smaller or equal to 300, and when this is kilopascal, you have to choose the units carefully, because this is meter, so your force will be calculated in kilonewton. So kilonewton divided by a square meter, that's kilopascal, right? So let's try this condition and see which one give you which one is more conservative. So this is 300. If I solve the first one, W should be smaller or equal to 3000 kilonewton per meter. If I solve this one, so 150 times 15, that is 2020. So which one of these conditions are more conservative? Bottom one, yes. So if you go with the bottom one, both of them remain under that stress. But if you go with the second one, AB would be okay, but CD would exceed that stress. So this is the right answer. So if you're not clear, please let me know. I'm happy to explain again. Say it again. All right. So the first thing you should note is the definition of stress, internal stress and internal load. There are different concepts. Internal stress, that means the distribution of the load. The unit, this is a mixed parameter. Mixed parameter, it depends on the load and reversely depends on the area. The larger the area, the smaller the stress. The larger the load, the larger the stress. But internal force, that is simply a simple variable, is a function of internal load. So here you have been asked to solve this structure. Okay, we know how to solve it, we know how to find the internal forces, but the question wants you to keep the stresses in each member below 300 kilopascal. So the first part is clear. You only have to solve this structure to find out the internal force in ABCD, but that is not enough, because we know the cross-sectional area of the bars are not equal. One of them is thicker, one of them is thinner. So as a result, you need to find out how the stresses are related to W, and then to keep them under, both of them under 300, that's a condition you have to investigate. So if I keep the stress in AB below 300, that requires the load intensity to be smaller than 3000. For the second rod, I shouldn't exceed W more than 2,250. So the second solution is more conservative because if I keep the W here smaller than 2,250, both members remain below the threshold. But if I go with this upper one, AB would be safe, but CD exceeds the stress above the limit. Can you talk louder, please? The area is square millimeter. A square millimeter, yeah. So shouldn't that be 200 millimeters? Okay, so all right, you're right. I assume that the area is meter square. So these are millimeter square. So kilopascal, kilopascal, that is Newton per square meter, and megapascal is Newton per square millimeter. So if I divide both sides by 10, that is kilopascal, is Newton millimeter meter, something like that. And so, or this is Newton per 1,000 per square. So that unit, um, if I solve, that is kilopascal. And yeah, well, one simple way of handling this is I multiply this by 1,000, and then these numbers grow, and that is Newton per meter. Minus 6? Yeah, because it's square. That that would bring this to the megapascal. If I that bring that to the pascal, but because this is kilopascal, I um, so that should be minus three here. Yeah. So that is W smaller than 3, and W is smaller than 2.25, and the unit is um, Newton per meter. All right, the next question we have is 7-8. So here the force is 300 Newton. And what about the area? The area is pi by 4. I'm calculating this in the square millimeter. That is, so these are the radius. These are not um, the diameter. That's pi RO. That's 100 squared minus 80 squared. That's the area. That is 11,000. All right, now the stress in megapascal, that is F in Newton divided by area in millimeter. That is, so this is 26.53. And the unit is megapascal, right? When you keep the forces in Newton and the area in the square millimeter, the outcome is megapascal. Agree? The next thing is you want to show the distribution of the stress over the cross section. So let me just show this as a cross section. All right, so this is my pipe. If I make a section, and then the stress distribution, I mean, the average stress distribution is like so. 26. Anyone needs clarification, or is that clear? You're not sure?
And does it just say it's 26.5 for the whole?
That is the distribution. That's a load intensity. That's load intensity. And then these kind of calculations for the average stress. I mean, in practice, you might have a stress concentration at the sharp edges, but here we are taking an average one. So the next one is 7-11. Let me know when you finish with this. Number 11. Can you see it from the back or you want to large? All right. Here you want to find the average normal stress at point A, B, C. And the diameter is not uniform. So the first step is you have to make a number of free body diagram to find the internal forces. And once you have the internal force, depending what the cross-sectional area is, at that point you calculate the average normal stress. All right. First thing first, I mean, that is not needed, but if I ask you to check whether this member is at the equilibrium, how would you check? How the sum of the forces horizontally should be 0, and that is true. Now, it doesn't matter which side you, I mean, I need one free body diagram at point C, one free body diagram at B, and one free body diagram at A. So if you are smart, for point C, I take the right-hand side free body diagram. Okay, that's the easiest free body diagram, and it has 200 Newton, and here I have FC. So FC is equal to 200 Newton. For B, it doesn't matter which free body diagram I take, right-hand side, left-hand side. At C, so at B, I go with the, again, right-hand side free body diagram. So the free body diagram would look like this one. 200 Newton and 800 here. FP. So FP is 600 Newton in compression. And 200 is this compression or tension? That is tension, right? And what about the last point, point A? At point A, it would be smart if you take the left-hand side free body diagram. I mean, both of them give you the same answer, but left-hand side is easier to solve. So that free body diagram would be 300 here and FA over here. Therefore, FA is 300 Newton, and that is under tension. All right, so now the next step is to find the average stresses. So for this one, sigma C average, that is 200 divided by 900 where? For the second one? Which diagram? A. All right, so that yeah, it won't come into the equation, right? If you take the left hand side, it won't come to the equation. I mean, with B, I took the right hand side, that didn't come to the equation, and in A, I'm only concerned about that envelope here, that envelope here. All right, just ask if you're not sure with anything, please ask. And then how do I find the area? The area, when the diameter is provided in millimeter, that is pi divided by pi by 4 and diameter squared, which is 25. And then what you get here, that is in megapascal, right? How do I know that's megapascal? Because the force is in Newton and the area is in a square millimeter. That would be megapascal. And then the outcome, that is in tensile stress. Tensile stress. So how should I go with B? So the average sigma at B, that is 600, and over here is pi by 4 and 10 squared, which is 100. And that is also in megapascal, but this one is compressive. And finally at A, my normal stress is 300 divided by the cross section over there is 5 again. Pi by 4, 25, and here you get megapascal, and that is tensile. So that was point. This was question 11. Next one is 12. All right, people ask me that in the final exam, do they have to read the stuff before the midterm or not? Well, I wish I could eliminate that, but free body diagram is something you need to know. All right, without free body diagram, we cannot. I mean, I don't give you question specifically from the topics before that, but I mean, how can you find the forces and stresses without knowing the free body diagram? Or still, you need to know this is a pin joint a structure, which parts are two force member, which parts are. I mean, if I want to solve that problem, what is the first step? Someone just give us a hint. How should we start with this one?
Figure out the stresses.
Before stresses. What is before stresses?
Draw a free body diagram.
Free body diagram to get what? Internal forces.
Yes, like
internal forces. Yes. And the best approach would be I take a free body diagram around A, right? So that is, I'm going to have one force with that angle, one force like that, and the only known force is 50 kilogram. So 50 kilogram, this is almost 500 Newton. And how do I solve this free body diagram? That is FAB, and this is FAC. One way of solving that is I can simply resolve that force into two components. That's the easiest way to do that, right? I mean, I could construct a triangle, but then construct a triangle, you have to use the sine law or cos law to solve it. But this is easier than that, because FAC, if I resolve that into y component, that is FAC times sine theta. Sine theta is 3 over 5. 3 over 5 is 0.6. And then if I resolve that horizontally, that is FAC time cos theta. Cos theta is 4 over 5, which is 0.8. And now that I resolved, I don't need that force anymore. I can get rid of it. Is that clear? So from here, the steps are straightforward because 0.6 FAC is equal to 500. So net forces vertically equal to 0. That is 6 over 10 FAC is equal to 500. And that FAC is 5,000 divided by 6. 833. And the unit is in Newton. So now FAB is equal to 0.8 FAC. That is 666.7 Newton. All right, now we managed to find out the internal forces. What should I do next? The diameter of AB is equal to 8 millimeters. So diameter of AB is equal to 8 millimeter. And then we are not concerned about the stress in AC. We only want the stress in AB. So that's all I need. So let's divide the stress in AB. That is FAB divided by pi by 4, 8 squared, which is 64. So that is 1326. And the unit is megapascal. Yep. Yep, that is net forces horizontally equal to 0. That is FAB is equal to 0.8 FAC, which is 833.3. So if you multiply that, it gives you this number. All right. Questions? All right, we go to the next page, 360. All right, this is the first one. I think the image might be a little bit confusing. This is 26. Yeah, 26. Let's do 26.
By volume element.
Sorry?
When it says volume element, it's located.
Volume element. Let me see. You are ahead of me. I'm still, I'm not there. Okay, so that is one way of saying the per volume.
I'll say like the stress test.
I think so. Yeah. Determine the average normal stress point and represent the stress on a volume element. No, no. No. Yeah, yeah. So what it says is it says carve an element from inside at B and show how these stress is oriented. Is this oriented on the side faces, on the top faces, on the front faces? Because once you do an element, I mean, this is just very, I don't like confusing a student like that. So what he means in general sense, you could have forces on either of these faces of the element. So this is X, Y, Z, and here all of these are normal stresses because the forces are perpendicular to the area. Also, you could have forces which are acting on these planes. So these are making shear stresses. So in this case, we are talking about the normal stresses. And then it wants you, when you find sigma D would be here on these two faces.
So all I want to know is which face.
That's what it means. I mean, yeah, it's just a represent your results, show that you know what you're talking about. All right, I think, can I bring this lower? Nope. It one more time. Oh, yes. Good. All right, so here I think with point B, that's straightforward because you take the left-hand side free body diagram. So I need to make two cuts. One cut I'm making here, that gives me sigma D. And then when I make the second cut at point E, that gives me sigma E. All right. At A, the only confusion is the thing confusing is that's a hollow bar. It's not a solid bar. So with that hollow bar, how do you calculate the area? That is the OD, ID, and then the area for that is pi by 4 outside diameter squared minus inner diameter squared. That's how you find the area for the hollow bar. And then whatever the force is, you divide that by this area. And then if I want to show that as an element, I mean the element is at the between that. I mean this is just you have a ring, and that element is cut from here. So that is sigma d, which is equal to FD, that is 4 kilonewton in compression, 4,000 Newton, and the cross-sectional area is 2028, that is pi by 4, 28 squared minus 20 squared. So that is how you calculate sigma D. But at point E, that is a solid bar. The solid bar, yeah, that has a diameter of 12. So when I make the free body diagram at E, it would be smarter to take the free body diagram from the right. So here, my free body diagram would be 8,000 Newton at C, and then you get Fe equal to 8,000 Newton. That is under tension. And therefore, the stress at E will be 8,000 divided by pi by 4 and 12 squared. So this is point E here. I can show this is element inside that rod. And then my stress is acting on this plane and this plane here. That is sigma E average. That's axial stress, axial normal stress. Forty-one. Hey, do you want to give this a go, or all right? 5 minutes. Okay, the first step is um, Abdullah, what is the first step? One, reaction forces. Okay. So if I want to find the reaction forces, I need to release that from the support. And here the forces are exposed. Um, so the weight of the timber is negligible, so we ignore the weight. That only would expose this is FCD, and that is FAB. And then you have 60 Newton here. So net forces horizontally doesn't give me any extra information. Vertically, that gives me two unknowns, but something more useful is net rotation with respect to A. So that is 6,000 times D is equal to 3 FCD. So therefore, FCD, that is equal to 2000 D. And what is the unit? The unit would be Newton. If I keep D as meter, so that one is in Newton, provided that D is in meter. Now, um, sorry? 6,000 D, that is equal to 3 times FCD. So I cancel 3 from both sides. That FCD is 2000 D. Yeah. And again, I take the net rotation with respect to point C equal to 0. That is 3 FAB is equal to 6,000 times 3 minus D. Correct? Because this length is 3 minus D in meter. So that is FAB is equal to 2000 3 minus D. The unit is Newton. All right. And also I know that so we want to make the stresses on both rods equal. So that is a stress in AB. I want to set that equal to stress in CD. So that, I mean, is FCD divided by pi by 4, and well, that is not needed because I've been given the areas. Area of CD, that is 8 square millimeter, is equal to FAB divided by 12 square millimeter. All right. Now, all you have to do is just plug the number FCD, that is 2000 D divided by 8 is equal to 2003 minus d divided by 12. So now I cancel 2000 from both sides, and then so that is d over 3, that is 3 minus d over, that should be 2, right? So that is 3d is equal to 6 minus 2d. Therefore, 5d is equal to 6, and d is equal to 6 over 5, which is 1.2 meter. Makes sense? And then this is just a rule of which area is smaller. The smaller area is CD. So to make the surfaces equal, the force should be closer to AB, not to the CD. If that's closer to CD, the force CD becomes larger. Nguyen, how many hours you slept last night? Roughly 7. Marginal. 8 would be fine, but at your age, maybe
Maybe 4.
4. 4 is luxury. Yeah, yeah. I know it is very hard, but hopefully soon you'll be happy. All right, 46. Let's go to 46. Okay, 2 megagram, that is a tasteless way of giving the unit. Um, yeah, well, that is, I think that's 2 tons, right? 2,000 kilogram. All right, now I have to make a free body diagram about point A, and that would cut through the AB and CD. So the forces here, I have 2,000 kilogram multiplied by 10, that is 20,000 newton, almost. And then you have FAB, and this is FAC. Okay, so the best way of finding the forces is, I think, if we can construct a triangle, that would do the job, right? Otherwise, I have to resolve the forces and two equation, two unknown to be solved. Maybe constructing the triangle is only the tricky part. Let me go 20,000 vertical, and then from top I draw a line parallel to AB. If that is parallel to AB, that angle is 30. And from the beginning of that one, I should draw a line parallel to FAC. So if that's parallel to FAC, that is 45. And then the third angle is 180 take away 75. That is 105. So this angle is 105 degrees. All right. Now that is 20,000, and that is FAC. So to solve this triangle, I use the sine law. That is 20,000 divided by sine 105 is equal to FAC divided by sine 30 is equal to FAB divided by sine 45. Correct? All right, so that gives me two solutions. FAC is equal to 20,000 times sine 30 divided by sine 105, and FAB, that is 20,000 times sine 45 divided by sine 105. So FAC, that is all right. So now we managed to calculate the internal forces, and then the next step is internal forces into internal stresses, the normal stress. So you have the cross-sectional area of each. They're in millimeter. Diameter of AB, that is 12 millimeter. Diameter of AC, that is 10 millimeter. All right, so I get the normal stress in AC, that is 10 352.8 divided by pi by 4, 100. And the normal stress in AB, that is 14,641 divided by pi by 4, 224. And the unit for that is megapascal, because the force is in Newton and the area is in a square millimeter.
Why is the second one 320? That,
The second one, you mean AB?
yeah,
That is 14,600.
after the area, sorry.
The area is pi by, the area for AB is pi by 4, 12 squared, which is 224. 12 squared is 224. Right?
144.
144. Yeah, yeah.
Okay. There we go, get that.
Sorry about that.
Okay.
Yeah. All right. So today we simply dealt with the demonstration of the normal stress. Normal stress could be either normal shearing stress or, I mean, average. We talked about the average stresses. Average stresses are either um, axial force divided by the area, which give you the normal stress, or if the force and area are coplanar, like what develops inside the pin. So you have a yoke joint. To separate that, the pin is subjected to the shearing stress because the force resisted by the pin and the plane at which the pin would cut, they are coplanar. That would develop the shearing stress. And these are simple members. The simple members, you can describe them by average stress. But when you go to the beam, there is no simplicity as such because due to the bending, the stress from point to point changes. So if that's a beam and this is the neutral plane, by going above or below the neutral plane, the stresses would change. So far, we have discussed the normal stress which developed due to the bending moment. Next week, I'm gonna take you through the shearing stress developed due to the bending. Okay. So that is all we had for this week. Make sure you're coming for tomorrow computer lab. You know where to go. That is TV 201, the same time as our normal class. I'll be single-handed, some very heavy stuff to deal. The technician has gone, so hopefully you'll help me there. Please be there. For those who haven't done their report, don't underestimate 20%. You cannot afford to lose it, right? The, the, the report, I did yours last night. Haven't you checked this? You got the full mark. Yeah. And any other concern, any question? Flynn, can I have a word with you, please? Just not? Oh, maybe it's hidden. I have to publish it. If I publish, all people get 0. I'm waiting for them to submit before I release it. Yeah? But, yeah. Hey, you got 10. 10 out of 10. Yours was not complete. I expected to see the screenshot from the web solver. That was not there. I marked that, yes. Do you want me to? Do you want to resubmit? If you're happy with what you got, that's fine. Otherwise, if you want a better mark,
Yeah, yeah, that one. Did you do like the table? Yeah. Those are Excel spreadsheets you do? Yeah, yeah. So he did do it, but he still put it in. Did you not put it in? I said so. Yeah. Can I see the other one? I'll show you one.
all right. For today, we have Nguyen, Aiden, Chaisal, and Abdullah, Ahmad. Nigel is away. See, Barnaby away. Flynn is here. Shah is here. Darcy is here. And Porty not here. Okay.
Yeah, he,
All right. I look forward to